Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Augustin-Louis Cauchy's 1822 Mémoire sur l'intégrale définie, a seminal work in the development of complex analysis, marks a pivotal moment in the rigorous foundation of calculus and the broader landscape of mathematical analysis. This treatise represents far more than a mere technical report. It embodies a paradigm shift, solidifying the concept of the definite integral and establishing complex analysis as a legitimate and powerful branch of mathematics. Its influence reverberates through various fields, impacting everything from differential equations to theoretical physics. Before delving into the specifics of Cauchy's contribution, it is essential to appreciate the mathematical climate of the early 19th century. Calculus, while remarkably successful in solving numerous physical problems, was built upon foundations that many mathematicians found shaky at best. The concept of infinitesimals, quantities vanishingly small yet somehow influencing finite results, remained controversial. Mathematicians such as Joseph Louis Lagrange sought to build calculus on purely algebraic foundations, attempting to banish infinitesimals altogether. Cauchy entered this arena with a different approach, favouring a more geometric and analytical rigor. He sought to define fundamental concepts like limits, continuity, and the definite integral with greater precision. His work built upon the implicit foundations laid by earlier mathematicians, including Jean-Laurent D'Alembert, who had grappled with the notion of limits, and Bernard Bolzano, whose unpublished work contained surprisingly modern ideas regarding continuity. However, Cauchy provided the explicit definitions and systematic application that transformed these nascent ideas into a robust framework. Cauchy's Mémoire sur l'intégrale définie focuses explicitly on defining the definite integral, the bedrock of integral calculus, in a manner far exceeding the clarity and rigor of his predecessors. He defined the definite integral of a function f of x from a to b as the limit of a sum. Specifically, he divided the interval from a to b into n subintervals designated delta x sub 1, delta x sub 2, up to delta x sub n. He then selected a value x sub I within each subinterval, the definite integral, as Cauchy defined it, the limit as n approaches infinity, with the largest of the delta x sub I approaching 0, of the summation from I equals 1 to n of f of x sub I multiplied by delta xr. This definition, while seemingly abstract, provided a solid foundation for understanding the definite integral. It replaced the intuitive notion of area under a curve with a precise analytical formulation. This meticulous definition provided a powerful tool for evaluating integrals and, more importantly, for proving theorems about integrals with a previously unattainable level of certainty. The Mémoire further elaborates on the properties of definite integrals, focusing on continuous functions. This restriction to continuous functions constituted a deliberate choice, allowing Cauchy to sidestep many of the pathological examples that bedeviled earlier attempts at rigor. He proved, for instance, that if f of x is continuous on the closed interval from a to b, then its definite integral exists. This theorem, now a cornerstone of real analysis, provided a theoretical justification for many of the techniques used to evaluate integrals. A crucial contribution of the Mémoire lies in its careful treatment of complex functions and their integrals. Cauchy extended the concept of the definite integral to functions of a complex variable, where the path of integration becomes a curve in the complex plane. This seemingly innocuous generalization had profound consequences, opening up a vast new realm of mathematical possibilities. In particular, Cauchy presented his integral theorem, a result of unparalleled importance in complex analysis. This theorem, in its simplest form, states that if f of z is an analytic function, meaning it is differentiable in a region of the complex plane C is a closed curve within that region, then the integral around C of f of z dz is z. This theorem, while elegant in its statement, has far-reaching implications. It allows one to evaluate certain real integrals with remarkable ease, by transforming them into complex integrals and exploiting the properties of analytic functions. It also forms the basis for many other important results in complex analysis, including Cauchy's integral formula. Cauchy's integral formula, a direct consequence of his integral theorem, provides a way to calculate the value of an analytic function at any point within a region, provided one knows the values of the function on the boundary of that region. Specifically, if f of z is analytic within and on a closed curve C, and z sub 0 is a point inside C, then f of z sub 0 equals 1 divided by 2 pi I times the integral around C of f of z divided by z minus z sub 0 dz. This formula demonstrates the remarkable connection between the values of an analytic function within a region and its values on the boundary. The immediate applications of Cauchy's work were primarily theoretical, solidifying the foundations of calculus and opening new avenues for mathematical research. However, the concepts and techniques he developed soon found their way into various branches of physics and engineering. For instance, the theory of complex functions and Cauchy's integral formula proved invaluable in the study of fluid dynamics, electromagnetism, and quantum mechanics. In fluid dynamics, complex potentials, derived from analytic functions, provide an elegant way to describe two-dimensional fluid flows. In electromagnetism, complex representations of electric and magnetic fields simplify the analysis of electromagnetic waves. In quantum mechanics, complex wave functions are fundamental to the description of quantum states, and complex integration techniques are used extensively to calculate probabilities and other physical quantities. The reception of Cauchy's Mémoire was not universally enthusiastic. While many mathematicians recognized the importance of his work, some were initially skeptical of his emphasis on rigor and his use of complex numbers. The concept of a complex function, differentiable in the complex plane, seemed abstract and divorced from physical reality to some. Furthermore, Cauchy's proofs, while more rigorous than those of his predecessors, still relied on certain assumptions that were later scrutinized and refined. For instance, his initial proof of the integral theorem required the assumption that the derivative of f of z is continuous, an assumption that was later shown to be unnecessary. Despite these initial reservations, Cauchy's work gradually gained acceptance and exerted a profound influence on the development of mathematics. His emphasis on rigor became the standard for mathematical analysis, and his theory of complex functions opened up a vast new area of research. Later mathematicians, such as Bernhard Riemann and Carl Weierstrass, built upon Cauchy's foundations, developing their own approaches to complex analysis and further refining the concepts of limit, continuity, and differentiability. Riemann, in particular, provided a geometric interpretation of complex functions, emphasizing the concept of conformal mapping and its applications to geometry and physics. Weierstrass, on the other hand, focused on a purely analytic approach, defining analytic functions in terms of power series and emphasizing the importance of uniform convergence. Cauchy's work influenced several mathematicians directly. Joseph Liouville, who made significant contributions to number theory and complex analysis, was heavily influenced by Cauchy's work. Liouville's theorem, a fundamental result in complex analysis, states that any bounded entire function, meaning a function that is analytic everywhere in the complex plane and bounded in magnitude, must be constant. This theorem, which has important applications to algebra and number theory, can be easily proved using Cauchy's integral formula. Another mathematician deeply influenced by Cauchy was Charles Hermite, renowned for proving that the number e, the base of the natural logarithm, is transcendental, meaning it is not a root of any polynomial equation with integer coefficients. Hermite made extensive use of complex integration techniques in his proof, drawing heavily on Cauchy's work. The Mémoire also had a direct impact on subsequent works in mathematical physics and engineering. For instance, the development of operational calculus, a powerful technique for solving differential equations, was heavily influenced by Cauchy's work on complex integration. Oliver Heaviside, a self-taught electrical engineer and physicist, famously used operational calculus to solve problems in electrical circuits and telegraphy. While Heaviside's methods were initially criticized for their lack of rigor, they proved remarkably effective in practice. Later mathematicians, such as John Bromwich, provided a rigorous foundation for operational calculus, drawing heavily on Cauchy's theory of complex functions. In conclusion, Augustin-Louis Cauchy's 1822 Mémoire intégrale définie stands as a landmark achievement in the history of mathematics. It provided a rigorous foundation for the definite integral, opened up the field of complex analysis, and exerted a profound influence on the development of mathematics, physics, and engineering. Cauchy's emphasis on rigor, his careful definitions, and his groundbreaking theorems transformed calculus from a collection of intuitive techniques into a solid and well-defined branch of mathematics. His work continues to inspire mathematicians and scientists today, serving as a testament to the power of abstract thought and the enduring beauty of mathematical analysis. It is a contribution so profound that the initial difficulty some experienced in fully grasping its implications now seems almost comical, a gentle reminder that even the most brilliant minds sometimes require a little time to adjust to true innovation.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.